without further ado.
Okay, thank you very much. So before starting the talk, I'd like to thank you all for the nice welcome and the interesting discussions I had before. And thanks for the opportunities to speak here. So I'll be talking on magnetic fields and rotations in core-collapse supernovae. This is the result of a collaboration between MPA and the University of Valencia, done together with Pablo, Ewald Müller, and Miguel Angel Loloy. A short overview of the talk. I'll start with an introduction to the subject of core-collapse supernovae, and in particular to Magneto-rotational explosions of supernovae, and then come to the main topic, namely simulations of field amplification by the magneto-rotational instability. So I'll just start with the introduction on supernovae. The progenitor of type 2 supernovae, core-collapse supernovae, is a massive star of more than roughly 8 solar masses, which at the end of its main sequence and post-main sequence life has an onion shell structure where a core consisting of roughly 1.5 solar masses of either iron or oxygen, neon, and magnesium is surrounded by layers of silicon and carbon, oxygen, and helium and hydrogen. This core is unstable against gravitational collapse and collapses to a proto-neutron star from an initial density of around 10 to 9 grams per cubic centimeter to more than nuclear matter density of, say, a few times 10 to 14 grams per cubic centimeters. So collapse proceeds within roughly a free-fall time, so a few hundreds of milliseconds, whereby 10 to 53 ergs, the gravitational binding energy, are released, mostly in the form of neutrinos. Then collapse stops due to the incompressibility of the nuclear equation of state, and an outwards traveling shock wave is formed. This shock wave stalls shortly afterwards because it loses a lot of its energy in dissociating iron nuclei to a gas of nucleons, basically. And then one of the main questions of supernova theory today is how this stalled shock wave is revived. A number of mechanisms have been proposed for this, which I'll give you an overview on the next slide, but to start with, I'll introduce what the ingredients to the problem are. First, it's important to note that this is a multi-scale problem. We have a vast range of length scales involved. The largest scale is the radius of the entire star, which may be a blue or red supergiant. Then we are, though, focusing mostly on the innermost region, a few thousands of kilometers in radius, which is roughly the radius of the pre-collapse iron or intermediate mass core. After collapse, this mass is concentrated within a few tens of kilometers. The proto-neutron star, still hot in temperature, has a few tens up to maybe 50 kilometers. The shock wave stalls at a radius of around a few 100, 200 or 300 kilometers roughly. Because of those huge scales and the very tiny dissipation coefficients, we have very large hydrodynamic and magnetic Reynolds numbers. Consequently, we have to cover a large range in length scales, and this corresponds also to a large range in timescales. The whole explosion may take place on, or in the core may take place on roughly less than a second, which is roughly 10 to 3 dynamical timescales of the proto-Newton star. In addition to this multi-scale problem, we have to deal with a multi-physics problem, because we have to include all these ingredients into modeling, basically multidimensional general relativistic, magnetohydrodynamics, turbulence, the largely unknown nuclear equation of state, a neutrino transport, which goes from the optically thick diffusion limit in the innermost regions to transparent in the envelope, and the most important physics is happening right at the transition from optically thick to transparent, which makes things even more complicated. Additionally, we may have nuclear burning and all those difficult neutrino-matter interactions. Consequently, in many cases you have to simplify the problem, which will be one of the main simplifications of the work we've been doing. So now the overview of the explosion mechanisms. It's important to note that this whole problem is not a matter of energy, because we have plenty of energy. The gravitational binding energy of the core is more than sufficient to unbind the envelope. But it's a problem of energy transfer. We have to, since most of this energy is released in the form of neutrinos, it's not accessible easily to the surrounding matter because of the small interaction cross sections of neutrinos. And though in some cases the classical spherical neutrino-driven explosion mechanism may work, where neutrinos diffuse out of the proto-Newton star and heat the matter right behind the shock. In a limited mass range of roughly 8 to 10 solar masses, where the collapsing core consists of intermediate mass elements rather than iron, and the star has a very steep density gradient outside the core. Explosions have been obtained for these mechanisms even in 1D by quoting the work by Francisco Chuquetauro at MPA, from one of Francisco's simulations, showing the as a function of time, trajectories of different mass shells during this collapse. You can see during the explosion, initially they collapse from roughly, this is 1,000 kilometers to proto-Newton star, sitting at 10 to 30 kilometers, and collapse. Here the proto-Newton star contracts still due to the release of energy, thermal energy by neutrinos, but at a certain point the accretion of matter, those mass shells, is reverted and the explosion starts. So this line denotes the shock radius, so you can see that it goes outward, and even more the matter behind the shock has positive velocity. So this is a successful explosion of such a star. The most important thing of this mechanism, except that it works, is that it's compatible with a standard pre-collapse evolution. You don't need anything which is not in this included in the standard models of stellar evolution, for example, rapid rotation or extremely large magnetic fields. The last point is true also for... This was 1D. Mm-hmm. They've done the same in 2D to see mixing processes, but the explosion itself is not dependent on 2D effects. Which is, however, the case for the multidimensional standard model, where you have the same physics as in the spherical case, but neutrino heating, but plus hydrodynamic instabilities. The most important ones are convection inside the neutron star or proto-neutron star, and the standing accretion shock instability, which is a result of a coupling between matter at the accretion shock and the proto-neutron star surface via acoustic and waves and entropy waves traveling up and down between the shock and the proto-neutron star.
It's not clear actually how much neutrino heating leading to convection is actually driving this instability of the shock versus this linear feedback mechanism.
Mm-hmm.
There's some debate going on about this, and it may depend in part on how rapidly the neutrino sphere is contracting.
Yes.
So the work that has been done on arguing for a linear instability has either made some very drastic simplifications
Mm-hmm.
of physics,
Yes.
or there's been a very strong assumption about how rapidly the neutrino
Yes.
sphere is contracting. Anyway.
Mm-hmm. So, as shown in these simulations by Andreas Marek from MPA, this whole mechanism may work for simulations for initial progenitor masses of 11 to 15 solar masses. This actually is a simulation of a 11.2 solar mass star. You can see how this instability deforms the shock wave very strongly. It's far from spherical. This inner region is still roughly the proto-Newton star, whereas the shock wave has in this case, a very prolate appearance, which is probably an artifact of the 2D geometry. But it is not clear how well the same mechanism works for higher mass stars. And still, it's also not yet demonstrated that this is extremely robust. Thus, there's still some debate about additional.
Would they recover the same instabilities with the same code, with the same setup?
What do you mean? Sorry.
So I've seen simulations like this where they seem having instabilities.
Mm-hmm.
They're using the same code with the same setup. They wouldn't see them again when they run the same simulation. I'm just wondering if it's the case here.
I mean, using this code, which has all of the detailed neutrino microphysics included, it's not an easy task to run, for example, a large number of simplified models to investigate the instability in more detail, but with basically a code which uses the same hydrodynamics, but much simplified neutrino transport. Leonhard Scheck has studied the Sarsi instability in more detail, and there it works. Now come to more exotic, or partially more exotic explosion mechanisms. Namely, one is energy transfer by waves, where you transfer energy generated by accretion at the proto-Newton star output to the shock by means of different kinds of waves. For example, the acoustic waves proposed by Adam Burrows and collaborators, or as recently proposed by Suzuki, Yamasaki, and Yamada, Alfvén waves, which both could be generated near the proto-Newton star. This shows a simulation of Adam Burrows. Proto-Newton star is located here. Accretion, in this case, generates G-mode, unstable G-modes near in the core, from which then acoustic waves travel upwards and deposit energy near the shock wave. It's not fully clear, in particular not for this second Alfvén wave mechanism, how successful explosions in this case are. The first mechanism, acoustic waves, is probably compatible with stellar evolution theory, whereas Alfvén waves, in this case you have to rely on magnetic field amplification. And the last mechanism I'll talk about involves rapid rotation. Since the energy transfer is a problem, you could think of going to a form of energy which is more accessible than neutrinos. And for example, one of these forms would be rotation. You can tap into the rotational energy by magnetic fields relatively easily. So if you use fast rotation and impose strong magnetic fields, you get explosions relatively easily. The problem, though, is how realistic these explosions are, because rapid rotation is probably present only for certain stars, and strong magnetic field is also rather uncommon, plus the fact the probability to have both rapid rotation and strong magnetic fields is not too large. Consequently, you have to rely, for example, if you consider a fast rotator on efficient field amplification. And for this, Akiyama et al. Have proposed the Magneto-rotational instability to work also in supernova cores. Now, a few words in more detail on this Magneto-rotational mechanism. There are a few different possibilities. For example, you could have small-scale MHD turbulence leading to an effective viscosity and to small-scale transport of angular momentum. Or the same can also be done by large-scale fields. In any case, if you have angular momentum transport from the inner core of a rapidly rotating proto-Newton star, you lose centrifugal support, and the previous core roughly in rotational equilibrium has to contract, which we have seen in very simplified simulations of magnetorotational collapse. What you can see here is as a function of time in milliseconds, the maximum density of the core. The dashed line is without magnetic fields. The solid line is with magnetic field. Due to off the bounds, which is at roughly 48 milliseconds, the non-magnetic model remains in equilibrium and nothing more is happening except for oscillations. In case of magnetic fields, strong magnetic fields, we have the transport of angular momentum leading to the loss of centrifugal support and consequently a contraction of the core on secular timescales. This was done with large-scale fields, and a similar thing as Adam Burrows has done, though with a much more refined microphysics. In this case, you get, as a very prominent feature, bipolar explosions, even jet-like ones, where collimation may be done due to magnetic stresses. All of this may, of course, be important potentially only on longer time scales.
But all the calculations that show the jets put in some very strong
Exactly.
magnetic field, right? I mean, there is no calculation which would have to be essentially 3D starting from a weak orbital magnetic
Exactly.
field plus strong rotation, showing you would actually get a bipolar explosion.
Yes. So in this sense, both regarding the field strength and the field topology, those models, all the ones we have done and the ones by Adam Burrows, use a relatively unrealistic initial setup.
So how strong is the magnetic field?
In this one, it was initially 10 to 11 Gauss.
Pre-collapse.
Pre-collapse. And
So then you can get anything during collapse.
So it's something like 10 to 16 Gauss post-collapse.
and stellar evolution, on the other hand, predicts roughly up to 10 to 9 Gauss in the toroidal component, and perhaps 10 to 6 in the poloidal one, or even yes.
I don't think you should believe any of that.
So it's probably an upper limit.
I know you're convinced.
Okay, so again, this has already. So the crucial point has already been mentioned. We need very strong magnetic fields. And typical pre-collapse fields are too weak. So either we have to use a special class of progenitors, which may or may not exist, or we have to rely on very efficient field amplification during and after collapse. Now, those are the main field amplification mechanism. During the infall, during the collapse, you get, of course, flux freezing compression, which gives you maybe 2 or 3 orders of magnitude in field strength. Afterwards, if you have differential rotation, the magnetic energy can be increased by winding of field lines, leading to a linear increase of the field strength. And furthermore, you can have different kinds of hydromagnetic instabilities which feed off the energy in the differential rotation, as in the case of the Magneto-rotational instability, or as in case of convection, feed off entropy or composition gradients. Now, of those amplification mechanisms, the last one, the instabilities, is particularly interesting because it leads to exponential field growth. And as we start from very tiny initial fields, probably a linear growth is not sufficient to lead to strong fields within the times we require them. Thus, we I focus here a bit more on the MRI. It is a local linear hydromagnetic instability of differentially rotating fluids with a weak initial magnetic field. The mechanism behind the MRI is basically the runaway of angular momentum transport along magnetic field lines, and the instability criterion is a negative gradient of the angular velocity. If the progenitor star rotates, after collapse, it will rotate probably differentially, even if the rotation initially was rigid. And this criterion, a negative omega gradient, is fulfilled typically in a proto-Newton star. The growth time, if the instability criterion is fulfilled, is roughly the rotational period. And for example, in accretion disks, it's important that the MRI leads to MHD turbulence and efficient transport of angular momentum, enabling accretion onto the central object. So the main application of the MRI is, of course, the accretion disk, where you have Keplerian shear leading to a hydrodynamically stable, Rayleigh stable system, and which is nevertheless MRI unstable. It's Rayleigh stable because the angular momentum increases outwards, but it's MRI unstable because of the negative omega gradient of the system. the MRI grows very rapidly on rotational timescales and leads to MHD turbulence. The system is relatively well studied, but still not fully understood. And now comparing this to supernovae, we have to deal with a similar but not the same physical system. We may have differential rotation, but we have probably also an important thermal stratification, which may lead to additional stabilization or destabilization. So in the most extreme case, we have a system which is hydrodynamically unstable and MRI unstable, but all combinations are possible. Now we have to ask ourselves the question, is the growth fast enough, and does it lead to strong enough fields? Now, to study this, we have performed both the analysis of the instability criteria in a supernova course and simulations of MRI unstable systems. And I will, in the following, report a bit on the results from these two studies. The instability analysis, for this we have taken results obtained by Balbus in 1995 and Urpin 1 year later. They did a local linear analysis of perturbations of a hydrodynamic background in equilibrium, some differential rotation, some entropy gradient, adding a weak magnetic field and examining the dispersion relation of MHD waves. And this is what you get in this case. First, the symbols I'm using here in this plot. This is N is the buoyancy frequency, and this is the radial gradient of omega. So C is a measure of the combined thermal and rotational instability, the Alfvén velocity and the wave number of a mode. Additionally, the angle between a particular mode and the rotational axis. Now, plot a bit more in detail. This is this C, the combination of buoyancy and rotational instability, and hope it's not very easily seen. This is basically the K is missing. It's K times the Alfvén velocity. So long modes are up here and are down here, and short modes up here. You can see at first there's a stable branch, a branch of stable modes. Those are the very short modes. They are stabilized by magnetic tension. The variable color-coded is a relative a normalized growth rate, and so we have below this line unstable modes with a certain growth rate, and we can distinguish between two different modes: the Alfvén modes, which are more or less the classical MRI modes, which grow fastest in a particular space of wave numbers, and the buoyant modes, which resemble convection, which grow fastest over basically from the unstable threshold to lambda equals infinity. This fact that these Alfvén modes grow fast only in a limited range of wave numbers or limited range of wavelengths is what's so troublesome in numerical simulations of the MRI in supernovae, because in a global simulation you have to cover both the global scales of 1,000 kilometers and those scales, and these can correspond to centimeters even So you would need to use a very fine grid, which you can't afford, especially not in 3D.
So what's the horizontal axis C is C of -1 means it's stably stratified, or what?
No, stable stratified is
Positively.
yeah.
So they are all unstable.
You have the instability, but the instability changes changes its character at this line. You have only those Alfvén modes here and only those convective modes here.
But in the stable regime, why do we get convection anyway?
Sorry?
But they are all, the whole plot is convectively unstable.
Not necessarily. It depends on this ratio between n and the omega gradient. I'll show it here. Here you can see what kind of instability you get in different regimes. This is again buoyancy, and this R is the gradient of omega. So depending on whether you have a strong thermal gradients or strong omega gradients, you can get, for example, ordinary convection, the standard accretion disk, magneto-rotational instability, which we called in here magneto-shear, hydrodynamic Rayleigh instability, or some mixed regime. Those modes characteristic for this and this regime are the Alfvén and the buoyant modes, respectively. And the regimes which are most important to supernovae probably are somewhere here, mostly likely convection, the mixed ones, and possibly also the magneto-shear regime. Now, again, to introduce a bit to the kind of simulations we have been performing.
Does this depend on the height of your accretion disk it forms?
Oh, it doesn't form an accretion disk. We are still in a roughly spherical core. Under such conditions, of course, it depends on the latitude at which you are. But furthermore, of course, it depends also on thermal gradients, which are contained in N. So there's all those entropy or composition gradients, and on the other hand, the omega gradients are contained here. So probably it depends, of course, also on things like the scale height and all those thermal length scales and time scales.
So the boundary between the blue stripe and the green area at the bottom of the plot is the Rayleigh stability boundary.
This is the Rayleigh. Mm-hmm. Okay, as said before, this is probably showing you the resolution problems we are facing. We have to deal with the global scale, which, depending on whether or not we are simulating the whole domain or possibly only the proto-neutron star, is from a few tens to 10,000 kilometers. Typically scale heights of pressure or similar quantities are of the order of 1 kilometer at the proto-neutron star, whereas the MRI wavelength, which we would like to resolve to get all those nice rapidly growing Alfvén modes, is of the order of a few centimeters or meters, and of course the dissipative scales are far below. So we have here are those physical scales, and now we have to choose a numerical grid which can capture at most, say, 1,000, a factor of 1,000 in length. So you have to place your 3 orders of magnitude which your numerical grid covers. Somewhere, for example, in a global simulation, you try to cover the global dynamics, but then you cannot resolve the MRI wavelength. Consequently, you can try to shift this MRI wavelength into a regime where you can resolve it, as this depends on the initial field. This means increasing the field, the initial field, by several orders of magnitudes, which is unrealistic, but at least then you can see the growth of those modes. On the other hand, if you try to use realistic initial fields, you can try to do a local computation covering at most a few scale heights of the problem, plus the MRI wavelength. Of course, even in this case, you won't be able to simulate the dissipation correctly. Then, unfortunately, you have to deal with the numerical issues as well. The boundary conditions, periodic or shearing periodic, which may have an influence on the simulations, and of course you get a huge parameter space. In those simulations, we have done such an approach using small boxes located near the equator of an unstable the unstable region of a core, and followed those in using a fine grid resolution. This is how we've done it. Code included this physics, ideal MHD. We're using full compressible MHD rather than the partially linearized shearing box equations. A simplified equation of state, external gravity, no self-gravity of the fluid, which you can neglect in such a local approach. No neutrino transport. These equations were solved using Eulerian conservative code with high-order reconstruction methods of the monotonicity preserving type, and with approximate Riemann solvers. To keep the divergence of the magnetic field 0, we used constraint transport. So it's relatively standard methods in total. And the models we simulated were small boxes, a few kilometers, covered by a grid with a resolution between 60 centimeters and 40 meters. Initially in hydrostatic rotational equilibrium, endowed with a uniform or a field or a sinusoidally varying field with a vanishing net flux, done in 2D axisymmetry or 3D. Now, these are basically the results. This shows you the temporal evolution. This is time in milliseconds of the mean magnetic energy. It's the logarithm of the mean volume average of the magnetic energy. The different lines and colors correspond to different components. What you can see here is the linear or exponential increase of the magnetic energy of the radial component of the magnetic energy during as the MRI grows, and afterwards the saturated turbulent state, which is characterized by significant amount of oscillations.
And these different curves, are you saying the different components?
Yes. For example, this one, the black one is the total magnetic field. This green is the vertical component, and the other ones are radial and phi component, plus the mean Maxwell stress component R phi, the product of B radial and B phi.
You said vertical and radial as distinct things.
Sorry?
You just said vertical and radial as distinct components of the field.
Mm-hmm. Okay. We were using cylindrical coordinates, radial and Z, and by vertical I meant the Z component. As
Basically parallel to the rotation.
exactly.
So using the flux correcting scheme plus the CT scheme, right? Are you using the consistent method of characteristic with the CT or the CT?
It's CT. It's more or less standard.
You're not using the C-box.
Sorry, then? I didn't.
Because if you don't use the method of characteristics,
Oh,
you are
no, not. I'm using CT with
using
rock.
those,
Mhm.
because there's so much efficient magnetic field that is out of nowhere.
Does it? I mean,
It's one of the problems. Anyway, gives you a perfect divergence. It preserves whatever initial divergence you
Yes.
have, right?
Yes.
It's very good for that. But then if you want to do the system method characteristic with that, you get this spurious magnetic field.
I mean, of course we have tested the code before, and so.
What is the peak magnetic field at 10 to the 29? What's that in beta?
It's in beta. It's roughly 10 to minus 2 or 3. Sorry, 10 to 2 or 3,
That's 1% magnetic energy.
roughly, at most. Okay.
So what's the maximum field strength here? What's the-
Roughly 10 to 15 Gauss.
And what are you assuming for the brunt?
In this particular model, the entropy gradient was 0.
0 brunt.
But we've done the same for all of those regimes, and we've confirmed all of the growth rates which we obtained from linear analysis for all of those regimes. Now, this, which is shown here, a number of computations, a comparison between analytic growth rates, those vertical horizontal lines, and simulations in the symbols. As you increase the resolution, which is going in this direction, we converge to the correct growth rate. And this is a 2D plot showing how those models look like. You get what's plotted is the current density, and you can see those pairs of upflows and downflows with very strong currents. Those are the so-called channel flows of MRI, which are characteristic. This Z and radial. Those are characteristic of the initial phases of the exponential growth of the instability. Basically, those are pairs of upflows and downflows with alternating magnetic fields. Later on, those channels break up and the growth terminates. And this is one of the main results, showing the Maxwell stress tensor at the moment of termination as a function of field strength. You can see for different models with different field strength, different resolutions, relatively clear trends of M as a function of B, or grid resolution or the rotational profile. For example, if you have a stronger initial magnetic field, you get a higher termination value of the Maxwell stress. If you have finer grid, you get similarly higher Maxwell stresses. Now,
Could you go back to the previous line? So the rotational profile, if it's slower, you get a higher
Yes.
Maxwell stress. But that has to have some limit because
Sure.
ultimately you're feeding off shear. So in a regime where resolution is playing a role, you find this inverse relation, but what extent is that just a function of resolution?
It is, I mean, maybe I'll explain where this comes from and then discuss. No, what we found is that this moment of termination of the growth is determined by the breakup of these nice channel flows by secondary instabilities. Those were found parasitic instabilities, as Goodman and Schur termed them. Right? The plots here are taken from this paper by Latta et al., which show different kinds of these instabilities. They are either distinguished as Kelvin-Helmholtz or tearing modes, or as those authors did as kink or pinch type instabilities. And we found that the growth terminates when those instabilities grow to the same, roughly to the same amplitude as the MRI has grown, or when, alternatively said as when they grow faster than the MRI. Now, this is how it looks like in our simulations. The initial state is a pair of those channel flows, upflows, downflows, plotted as radius z. Here in the lower half, the current density, and here the radial magnetic field. You can see very well those very ordered, coherent channels, which after a very short time scale, between all those snapshots are I think 0.05 milliseconds roughly. They break up into what looks very strongly like a tearing mode. And now to understand this termination level, and also in particular the relation with omega, slower rotation leads to stronger termination. We try to understand the dynamics of those instabilities by performing auxiliary simulations of roughly a model of those channel flows to understand how these resistive instabilities grow. And those were what we found there. Wider channels tend to give us slower growth of those instabilities. Stronger fields lead to faster growth. Finer grids also, because of the decreased numerical resistivity, lead to a slower growth. Now we know, on the other hand, the properties of those channel flows. The width, for example, is roughly given by the MRI wavelength. And those explains, for example, why a slower rotation leading to wider channels, and thus slower growth of those tearing modes, leads to a higher termination amplitude. And similar it's for weaker initial fields. Those lead to thinner channel flows and correspond then to faster growth of the of the secondary instabilities. And combining those two, those properties of the channel flows and properties of the instabilities, we could find some explanation of the scaling we observed. Now, if you remember the plots before, they had a pretty large scatter. Now, if we take into account all those scaling relations we determined from those auxiliary simulations, we get a nicer scaling of all those quantities, for example, and a much reduced scatter, which suggests at least some that we have at least tried to find some explanation here. Now the same. This was all basically that. There's.
Well, can we just go back to this claim that the magnetic stress grows as you decrease the rotation? Because the peak growth wavelength for an MRI is basically the Alfvén moment.
Mm-hmm.
And so the alphane crossing time across that layer, which would determine the characteristic reconnection time, is basically scaling with the rotation period. Right? So why is there, then I guess it's not clearly intuitive why there should be a net dependence on the rotation. I mean, if your reconnection physics is really in some sort of high magnetic Reynolds number scaling regime, where doubling or tripling the scale won't make much difference to the reconnection rate in units of the alphane crossing, right? And then why should changing?
The thing is, what's playing a role is not only the alphane crossing across the channel flow. The scaling is a bit different. You get some exponent. The growth rate of these parasites depends on the alphane crossing time to some power. And then it doesn't cancel out. And
Okay, I'll ask you that first.
okay.
So were you able to get the growth of the Tyrian mode?
Sorry?
Did you see the Tyrian mode growing in your solution?
At least we have some indication that we did.
Just use Rutherford equations and only the Q factors.
I mean,
This could be a numerical connection.
it is.
It is.
So yes.
Okay, so this numerical connection leads to Tyrian mode. You should get a scaling that mimics turbulence, right? Exactly. Yeah. So you see it?
I mean, we haven't investigated, for example, the power laws in detail, but those scaling we determined were not exactly the same, but very similar to what we would expect from reconnection theory. And
Anyway, the first test is the way to delineate between numerical connection versus true Tyrian modes.
Sure, that's true. Now, again, a few words then to what happens after termination. We have a turbulence state and efficient transport of angular momentum. This is shortly before a 3D model shortly before termination and now afterwards. So a very tangled and disordered magnetic field, which is visualized in color and field lines. Though we have still coherent structures, for example, filaments. You can see here the vorticity and the magnetic field strength with clear flux tubes. Overall, in time, what's plotted here is as a function of time. Averages of the toroidal magnetic field on slices of constant z coordinate, and you can see here in this plot very nicely that we have structures which are coherent both over relatively large scales in length and over several rotation periods. Rotation period is roughly 2 milliseconds here.
So what would that happen if the most unstable mode has a kVr thing equal to 1, meaning that if you start off with it should be a very small scale field given by your dynamical time. So how did you end up with these large fields?
This, I mean, what you get in with each of those general reconnection events, you basically those channels merge. This gives you an increase in the vertical scale, which is one of the factors contributing here, and then the whole nonlinear dynamics of this is still not fully understood. So
you're saying you're seeing a dynamo?
it's tempting to say it's a dynamo, but it's not yet.
You just thought
Clear.
you're making magnetic flux.
No. Due to the periodic boundary conditions, it's limited. Mm.
So do you enforce the shear or do you let it relax?
It can evolve over time.
Okay. Do you find the shear going away?
Well, partially at least. Not fully, but
And so what's the time scale over which the shear relaxes? What are you going to show us?
it's roughly this whole evolutionary timescale of several tens of rotation periods.
It's the only physics time scale is basically a rotation period.
What is rotation period again?
Roughly 2 milliseconds in this case. Now, finally, as a summary, I'll show you what we may have learned from this exercise. I've told you the explosion mechanism is very complicated. It involves all kinds of combinations of neutrino transport, instabilities, perhaps magnetic fields, but those only if we can amplify them from the weak fields by, for example, by the MRI very efficiently. And to investigate this possibility in more detail, we have studied the MRI by an analysis of the dispersion relation and simplified simulations. What we have found is that all those regimes identified in the dispersion analysis are confirmed numerically, and the instability tends to grow in typical conditions of post-collapse cores, but the instability can be quenched by parasitic instabilities. So, consequently, the results suggest that the MI may be important in supernova cores, but there's still a long list what we have not yet understood. For example, the physics of the saturation, not only up to the termination of the growth, but the long time scale afterwards. Is it really the dynamics of linear MRI modes and linear parasitic instabilities, or is it rather the nonlinear interaction of different modes of the MRI as suggested by this paper recently? The second important point is basically what can we learn from shearing boxes which replace the global dynamics by rather artificial boundary conditions. For example, in simulations of shearing boxes done by Froment and Papalouissou, an interesting dependence of the saturation and the occurrence of turbulence, here marked with yes or no, if there is or is not turbulence, depends very strongly on viscosity and resistivity.
Those had no vertical stratification.
They had no vertical, no.
Which you do.
Mm-hmm. Exactly. So they have shown here. They show here as a function of Reynolds number, magnetic Reynolds number, whether or not they get turbulence, and this is still not fully understood. It may be an artifact of the shearing boxes, or it may not, or it may come from something completely different. So it's questionable what we can learn from those shearing boxes. And then, as shown in this plot before, perhaps we have a dynamo. It has to be investigated in more detail. And thus, this is what we hope to do. So we have to do high resolution, now also global modeling, and to understand better the physics of the instability. So, and that's it. And thank you very much for your patience, and